Hello there, and welcome. Tonight I want to take you somewhere. Not somewhere far away, though we will journey billions of light years into the cosmic distance. Not somewhere frightening, though we will venture into spaces so extreme that the very laws of physics seem to bend and strain at their limits. No, tonight I want to take you somewhere deeper than distance, somewhere more intimate than the usual documentaries you might have encountered before. I want to take you into a quiet conversation about one of the universe's most beautiful mysteries, one that has puzzled scientists for decades and continues to reveal new wonders each time we look more carefully. Before we begin this journey together, I'd like to pause for just a moment and say something that I truly mean. If you're enjoying this cosmic exploration with me, if there's something about the mystery of the universe that calls to your curiosity and your sense of wonder, I would be deeply grateful if you would like this video and subscribe to our channel. Your support helps us continue bringing these contemplative journeys to people like you, people who want to think deeply about the cosmos while the world around them grows quiet. And if you're watching from somewhere specific in the world, or if you're watching at a particular time, I'd genuinely love to hear where you are and what time it is in your part of the world. Drop that in the comments below. Let's build a community of cosmic explorers, all gazing upward at the same stars from different corners of this beautiful planet. We would love to know what part of the world you're in right now, whether it's morning or night where you are, and most importantly, what drew you to this exploration of the cosmos. Your voice matters, and your perspective enriches this entire community of dreamers and thinkers who find solace in contemplating the universe. Now, let me ask you something, and I want you to sit with this question for a moment before we explore it together. What if I told you that somewhere in the distant universe, so far away that the light reaching us today began its journey when Earth was young, when dinosaurs still roamed our world, there exists an object so impossibly bright that it outshines an entire galaxy, not just outshines it, not just slightly brighter, but shines with the brightness of 1 trillion of our suns, all coming from something smaller than our solar system. It sounds like something from a myth, doesn't it? Like the kind of cosmic exaggeration that ancient astronomers might have imagined in their wildest dreams. And yet, it's real. These objects are called quasars, and they might be one of the greatest paradoxes that the universe has presented to our scientific understanding. The name itself, quasar, comes from the original term quasi-stellar object, because when astronomers first spotted them in the 1960s, they couldn't believe what they were seeing. These things looked like stars, mere pinpoints of light in our telescopes, but when scientists measured their properties, they realized they were something far stranger, far more distant, and far more powerful than any star we had ever studied. It's a question that might prompt some initial doubt. How could such a thing exist? How could the laws of physics allow for such extreme concentrations of power? But that doubt, that skepticism, is exactly where all good science begins. And in that space between doubt and discovery, between our comfortable understanding of the universe and the strange reality that observations reveal, there is a profound beauty waiting for us. There is wonder. What if, just maybe, these impossibly bright objects could teach us something fundamental about how the universe works? What if they could show us processes so extreme, so energetic that they reveal the deepest nature of gravity, energy, and light itself? What if, in understanding these distant cosmic beacons, we might understand our own place in a universe that is far stranger and far more magnificent than we ever imagined? That's the conversation I want to have with you tonight, and as we settle into this exploration together, I hope you'll find that the question of why quasars outshine entire galaxies is not just an astronomical puzzle, but a gateway to understanding the fundamental nature of reality itself. To truly appreciate this mystery, we need to first understand something fundamental about how we see the universe and our place within it. When you look up at the night sky, on a clear night, far from the lights of cities, when the stars stretch across the darkness in their full magnificent profusion, you're seeing light that has travelled enormous distances to reach your eyes. That light left those stars years ago, sometimes hundreds of years ago, sometimes millions of years ago. The further we look into space, the further we look back in time. This is not metaphorical. It's a literal truth about how our universe works. There's something almost magical about this realization, isn't there? When you gaze at a distant star, you're not seeing it as it is now. You're seeing it as it was. You're looking into the past. Every star you observe on a clear night is a window into a different moment in time, and the distance that light has travelled tells us exactly how far back we're peering into the cosmos. Think about this for a moment, and let it settle into your mind gently. The nearest star to our Sun, other than the Sun itself, is Proxima Centauri. It's about 4.24 light-years away. That means the light leaving that star today will not reach us for another 4 years and 3 months. If we wanted to visit Proxima Centauri with our current fastest spacecraft, it would take us roughly 73,000 years. We would need to travel for longer than recorded human civilization has existed just to reach the nearest star. And that's just our cosmic backyard. That's the neighborhood surrounding the Sun. When we begin to look further, when we extend our gaze beyond our immediate stellar surroundings, the numbers begin to become almost incomprehensible. The distances involved begin to strain our ability to visualize them, yet these distances are real. They're not exaggerations or flights of fancy. They're measurements, observations, facts about the actual structure of the universe in which we live. Now, galaxies are vast collections of hundreds of billions of stars, all bound together by gravity into organized structures that are among the most beautiful objects in the universe. Our own galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars, though the exact number is difficult to determine. These stars are distributed throughout the galaxy in a disk shape, swirling around the galactic center in what we call the galactic plane. When you look up at the night sky and you see that band of misty light stretching across the heavens, that's the Milky Way viewed from within. You're looking edge on at the disk of your own galaxy, seeing billions of stars so distant and so numerous that they appear as a continuous river of light. The nearest large galaxy to our own Milky Way is the Andromeda Galaxy, and it's 2.5 million light-years away, 2.5 million years. The light we see from Andromeda today left that galaxy during an era on Earth when our human ancestors were just beginning to use the first stone tools. It had been travelling through the absolute vacuum of space for millions of years at the fastest speed anything can travel, the speed of light, which is about 300,000 kilometers per second, and it was only just now reaching our eyes. We can see this entire galaxy, a structure containing about 1 trillion stars, because of light that began its journey in our distant past. But when astronomers first detected quasars, some of them were vastly further away than even the nearest galaxies. Some were billions of light-years distant. The light from these objects began its journey when the universe itself was young, when it was only a few billion years old. We were seeing these objects not as they are now. They may have changed, evolved, or even been destroyed in the billions of years since that light left them, but as they were in the distant past. We were literally looking backward through time, witnessing a young universe through the ancient light of these strange, impossibly bright objects. And here's where the mystery deepens in a way that becomes almost poignant. Something so far away, something so distant that it takes billions of years for its light to reach us, appears to shine with a brightness that rivals or exceeds the combined light of billions of stars. How is that possible? What engine could be so efficient, so powerful, that it could shine so brightly across such unimaginable distances? What mechanism in nature could produce such an extraordinary display of energy? This is where our story begins, not with answers, but with a profound question that would take scientists decades to unravel. And I want to invite you to carry this question with you as we explore further together, to sit with it, to contemplate it, and to allow it to shape how you think about the cosmos. The vast architecture of galaxies is something that deserves our contemplation. Galaxies are not just random collections of stars scattered through space in an unorganized fashion. They are architecturally organized, held together by the immense gravitational pull of billions or trillions of stars, and often organized around something even more fundamental at their centers. This is a crucial point, because it sets the stage for understanding what quasars actually are, and why they're so important to our understanding of the universe. Most galaxies that we observe, in fact nearly all of them, seem to have supermassive black holes at their hearts. Not little black holes, mind you, because even a little black hole would be an extraordinary object with a mass equivalent to several times that of our Sun. No, supermassive. These are black holes with masses equivalent to millions or billions of times the mass of our Sun, all compressed into regions smaller than our solar system. Our own Milky Way galaxy, which contains between 100 and 400 billion stars, has a supermassive black hole at its center called Sagittarius A star, with a mass equivalent to about 4 million suns. This black hole is about as large as our solar system, but it contains the mass of millions of suns compressed into that relatively small space. The density is almost beyond comprehension. Now, when we imagine a black hole, we often think of it as a cosmic vacuum cleaner, something that simply sucks everything in and destroys it, never to be seen again. And while black holes are indeed regions of space where gravity is so strong that not even light can escape once it crosses a certain boundary, the event horizon, as we call it, the reality is far more subtle and fascinating than this simple picture. A black hole doesn't instantly destroy everything around it. Instead, it creates one of the most dynamic, violent, and energetic processes in the entire universe. The region around a black hole is not a quiet place. It's perhaps the most active, most energetic place that nature can create. When material, gas, dust, the remnants of stars, even whole stars that have wandered too close, gets too close to a black hole, it doesn't instantly fall in. Instead, it begins to orbit around the black hole, spiraling inward in what we call an accretion disk. This accretion disk is heated to millions of degrees as material rubs against material, as friction and the intense gravitational forces convert the gravitational potential energy of infalling matter into heat and radiation. The material in an accretion disk is moving at a significant fraction of the speed of light. It's under tremendous pressure. It's experiencing gravitational forces that would tear apart any normal object. It's a place of extreme physics, extreme energy, and extreme conditions, and this is where the magic happens, where we find the explanation for the quasar mystery. In these accretion disks around supermassive black holes, we find some of the most luminous, most energetic, and most remarkable objects in the entire universe. Some of these objects are so bright that they appear to outshine their entire host galaxies. They're called active galactic nuclei, or AGN for short. These are regions at the centers of certain galaxies where supermassive black holes are actively feeding on material, creating brilliant displays of radiation that can outshine the billions of stars that make up the rest of the galaxy. The brightest and most distant of these objects, those that appear to us as incredibly powerful sources of light across billions of light-years of space, are the quasars. The name quasar has become almost synonymous with the brightest and most distant of these objects, though the term was originally used because astronomers didn't understand what they were looking at. When they first spotted these objects in the 1960s, they looked like stars. They seemed to be stellar objects, but the more carefully astronomers studied them, the more obvious it became that they were something far different, far stranger, and far more remarkable than any star. If you were an astronomer in the 1960s, imagine the moment you first encountered a quasar. You're looking at data from a radio telescope, an instrument that detects radio waves from space, electromagnetic radiation that isn't visible to our human eyes, but that carries information about the universe in its own way. Radio waves are just another form of light, if you think about it. They're electromagnetic radiation, the same fundamental phenomenon as visible light, just with a much longer wavelength. You notice a radio source. It's interesting, but not unusual. Radio sources are scattered throughout the sky, and astronomers had been cataloguing them for years. Radio waves come from all sorts of astronomical objects, pulsars, supernovae, gas clouds, all sorts of things. But then something peculiar happens. When you point optical telescopes at the location of this radio source, trying to figure out what could be producing radio waves, you find something that looks just like a star. It looks like a star. It appears in your telescope as a point source of light. It has the spectral signature of a star, at least on first inspection. It appears to be a point source, something small and compact, something that doesn't extend across a large region of the sky. By all appearances, it's a star, but a star in our galaxy wouldn't be a strong radio source. A typical star produces very little radio emission. Stars produce most of their energy in visible light and infrared radiation. A star wouldn't produce the kind of radio waves you're detecting, so something doesn't add up. There's a contradiction between what the radio observations are telling you and what the optical observations are showing you. And then, when you measure the redshift of this object, the way its light is shifted toward the red end of the spectrum due to the expansion of the universe carrying it away from us, you realize something remarkable and deeply puzzling. you realize it's not a star in our galaxy at all. The redshift tells you how fast the object is moving away from us. Using the relationship between redshift and velocity, which is based on the expansion of the universe itself, you calculate the object's distance, and you realize it's moving away from us at a significant fraction of the speed of light, which means it's incredibly far away. It's not a nearby star, it's something out in the distant universe, perhaps billions of light years away. But if it's that far away, and it's appearing to us as bright as a star in our own galaxy, then it must be shining with an incredible amount of power. The mathematics are straightforward. Take the brightness we observe, account for how far away the object is, and calculate how much total energy it must be radiating. And the answer, when you work through the calculation, is staggering. This object is shining with the brightness of trillions of suns, billions upon billions of times brighter than our own sun. All of that power, all of that energy, presumably coming from a region of space not much larger than our solar system, or even smaller. It seemed impossible. It violated everything we thought we knew about how objects shine and produce energy. And yet, the observations were undeniable. The universe was presenting us with something that challenged our understanding of how nature works. I want to pause here and acknowledge something. If you're still watching, if this has captured your curiosity enough that you're staying with us on this journey, if the sheer strangeness of these objects has intrigued you and drawn you deeper into this exploration, I'd love to hear from you. What aspect of this mystery speaks to you most powerfully? Is it the sheer scale of the numbers, the incomprehensibility of such distances and such powers? Is it the paradox itself? How can something so small be so bright? Or is it the mystery, the sense that the universe still holds secrets that challenge our understanding and force us to reconsider what we think we know about reality? Drop a comment below and let me know what you're finding most interesting so far. This conversation is just beginning, and I want to know what draws you to these questions about the cosmos. What part of you responds to the mystery? What makes your mind want to understand these distant objects better? Because the truth is, quasars aren't just interesting as abstract puzzles. They're meaningful to us in ways that go beyond the purely intellectual. When we contemplate these distant objects, when we think about the vast scales of distance and time involved, when we grapple with processes so extreme that they challenge our imagination, we're engaged in something deeply human. We're asking questions about the nature of reality. We're wondering about our place in a universe that is far larger, far older, and far stranger than we normally contemplate in our daily lives. The astronomer Carl Sagan, who passed away decades ago but whose voice still echoes through the cosmos for those who listen, once said that the cosmos is within us. We are made of star stuff. The atoms in our bodies were forged in the hearts of stars and scattered across the universe in supernova explosions. And here, billions of years later, those atoms came together in just the right way to form beings capable of contemplating the universe itself. That's remarkable. That's something worth sitting with for a moment. That's something that changes how we think about ourselves and our place in the cosmos. The discovery of quasars and the gradual unraveling of their mystery is a beautiful testament to how human ingenuity and careful observation can illuminate even the deepest cosmic mysteries. It didn't happen all at once. It was not a sudden revelation, a eureka moment where everything suddenly became clear. Instead, it was a process, a gradual accumulation of observations, a conversation between theoretical physicists and observational astronomers, between bold speculation and careful measurement, between ideas tested against the reality of what nature actually does. In the 1960s and 1970s, several crucial developments converged to make quasar observations not just possible, but increasingly sophisticated and revealing. Radio telescopes had become more powerful and more precise, allowing astronomers to identify radio sources with greater precision than ever before. These telescopes could now pinpoint the location of a radio source to within a small fraction of a degree on the sky. Optical telescopes, particularly the new generation of large telescopes that were being built around the world, the Palomar Observatory, the Lick Observatory, and others, gave astronomers the ability to look at these objects more carefully and study them in detail. And spectroscopy, the technique of analyzing the light from distant objects to determine their composition, their motion, their distance, their physical properties, provided crucial information about what these quasars actually were. Spectroscopy works by splitting the light from an object into its component colors, like a prism creating a rainbow. Different elements produce distinctive patterns in the spectrum, so by studying the spectrum of an object, we can determine what it's made of. And the spectrum also tells us about motion, because moving objects exhibit a shift in their spectral lines due to the Doppler effect. The same effect that makes an ambulance siren sound higher pitched as it approaches you, and lower pitched as it moves away, also shifts the light from moving objects. This Doppler shift allowed astronomers to measure how fast quasars were moving, and, combined with other information, how far away they were. One crucial breakthrough came when astronomers realized that many quasars showed remarkable radio jets, streams of high-energy particles and radiation that extended far from the central object into space. These jets could extend for millions of light years, absolutely dwarfing the quasar itself. Here was something even more spectacular than the quasar's brightness. These jets were somehow being generated at the quasar's heart and projected outward at nearly the speed of light. They extended on scales that were almost impossible to comprehend. A jet from a quasar could be larger than 100 galaxies placed end to end, and yet it was being generated from a central engine that was smaller than a solar system. The jets themselves were not smooth and uniform. They had structure, they had bright spots and dim regions. They could bend and twist, they could interact with the surrounding material and create shock waves. Here was additional evidence that something extraordinary was happening at the hearts of these objects, something that could generate not just bright radiation, but also these powerful directed jets of energy extending across vast regions of space. But perhaps the most crucial breakthrough came from a theoretical perspective rather than from new observations. Physicists and astronomers began to think carefully about what mechanism could possibly produce the brightness that quasars were displaying. What physical process could convert matter into radiation so efficiently? What could create a quasar's power output? And the answer they arrived at through careful calculation and reasoning was that the only mechanism powerful enough to explain a quasar's brightness was a supermassive black hole. Not just any black hole, because even a stellar mass black hole, a black hole with a mass of a few suns, would be a remarkable object. But a supermassive black hole of enormous mass, surrounded by a disk of infalling material that was heating up to millions of degrees and releasing energy through radiation and through the generation of those relativistic jets. The theoretical work showed that gravity, operating in its most extreme form around a black hole, could convert matter into energy with a level of efficiency that no other known process could match. The E equals mc squared equation that Einstein formulated showed that matter and energy are interchangeable. At the heart of a black hole, with matter being crushed and accelerated to near-light speeds, a tiny amount of matter could be converted into enormous amounts of energy. It was theoretically sound. And the more physicists thought about it, the more it seemed to be the only possible explanation. The idea of a black hole had itself been controversial for a long time. Karl Schwarzschild, a German physicist, had worked out the mathematics for black holes in the general theory of relativity back in 1916, just after Einstein published his revolutionary theory. Schwarzschild showed that if you took Einstein's equations and solved them for the case of a perfectly spherical, non-rotating mass, you got solutions that described regions of space where gravity was so strong that nothing could escape. But for decades, nearly 7 decades, black holes seemed like mathematical curiosities. They seemed like interesting solutions to Einstein's equations, but perhaps not real objects in the universe. Many physicists thought they were probably only theoretical, that nature would never actually create such extreme objects. It wasn't until the late 20th century that astronomers accumulated enough evidence to convince the scientific community that black holes were indeed real, and that they might be much more common than anyone had initially suspected. The discovery of quasars, combined with other observations and theoretical work, was part of what shifted this consensus. If quasars needed black holes to explain their brightness, and if quasars were real, and the observations made it clear they were, then black holes had to be real as well. Throughout the 1970s, 1980s, and 1990s, observations accumulated. Radio telescopes discovered more and more quasars, cataloguing them, measuring their properties, studying their evolution. X-ray satellites, telescopes that detect high-energy X-rays from space, radiation that cannot pass through Earth's atmosphere and so must be observed from space, began to detect high-energy radiation from galaxies with active nuclei. Infrared telescopes revealed that some of these objects were hidden behind dust clouds, their visible light blocked by cosmic dust, but their heat signature gave them away. Each new observation added another piece to the puzzle. Each new telescope, each new wavelength of observation revealed something new about how these objects worked. Perhaps most importantly, astronomers began to realize that quasars were not just isolated curiosities, rare and strange objects that had no obvious connection to the normal universe. They were common in the early universe. The further away we looked, and thus further back in time, the more quasars we found. The universe in its youth seemed to be full of these brilliant objects. But in the local universe, around us today, in the present epoch of cosmic history, quasars were rare. We didn't see new quasars forming nearby. The ones we observed were old, their light having travelled billions of years to reach us. This suggested something profound about cosmic history. Quasars weren't eternal features of the universe that would always exist. They were a phase that galaxies went through, particularly in the early universe. Many of them had probably faded billions of years ago. The black holes that powered them were likely still present in the centres of galaxies today, but they were no longer active, no longer feeding on material in a way that created the brilliant display of a quasar. Our own Milky Way's central black hole, Sagittarius A star, shows signs that it was once more active than it is today. Perhaps, billions of years ago, our own galaxy hosted a quasar at its heart. Perhaps we are witnessing the remnants of an activity that peaked in the universe's youth and has now faded to something quieter. I want to take a moment and reflect on what we're doing here together, you and I, in this quiet time that you've set aside to explore these ideas. In our modern world, we're often encouraged to move fast, to consume information quickly, to jump from topic to topic in an endless stream of stimulation and novelty. But contemplating the universe, really contemplating it, sitting with the questions it raises, allowing the wonder to settle into our consciousness, letting the implications unfold slowly in your mind, this is something different. This is something slower, something more meditative, something that asks us to simply be present with our curiosity rather than rushing to the next thing. It's countercultural in a way. It's a rebellion against the pace of modern life. When we look at quasars, when we think about objects that are shining with the brightness of 1 trillion suns, when we contemplate the vast distances across which their light travels, when we think about the billions of years that light has been travelling to reach us, we're engaging in an act of imagination that connects us to generations of human beings stretching back through history. We are participating in the same activity that moved ancient humans to create myths about the heavens, that inspired philosophers to wonder about the nature of the cosmos, that drove early scientists like Galileo and Herschel and Newton to risk their reputations questioning the prevailing ideas of their time. We are asking the same fundamental questions that have always driven the human spirit forward. Where did we come from? What is the universe made of? What are we? Why are we here? And we're doing this with tools and knowledge that would have seemed like magic, like pure sorcery to those earlier thinkers. We have radio telescopes that can detect electromagnetic radiation from across the universe, instruments so sensitive that they can detect the heat from an object the size of a coin on the moon if it were hot enough. We have space-based telescopes like the Hubble Space Telescope and others that can peer at objects with a clarity that Earth-bound observers could never achieve, unhampered by the distorting effects of Earth's atmosphere. We have computers that can process vast amounts of data and extract meaning from it, that can simulate cosmic processes and test our theories against reality. And yet, the fundamental human response to the cosmos remains unchanged. We look outward, we wonder, we ask questions, we seek understanding, and in that seeking we find something meaningful. Understanding quasars is really understanding one specific moment in the universe's history, the moment when scientists finally grasped what they were looking at. It's like slowly focusing a blurry image until suddenly, all at once, it comes into clarity. Before that moment, quasars seemed like paradoxes, violations of the laws of physics. They seemed impossible. Physicists and astronomers couldn't reconcile what the observations were telling them with what they thought they understood about how nature works. It was deeply puzzling. But after that moment, after the theoretical framework fell into place and scientists understood that quasars were powered by supermassive black holes, quasars became understandable. They became explicable, though they became no less wonderful. They transformed from being violations of physics into being exemplifications of physics. They became examples of how gravity, operating in its most extreme form, could create the most powerful objects and processes in the universe. They became illustrations of the deep truths embedded in Einstein's theory of general relativity. The fact that such extreme objects exist, the fact that gravity can concentrate matter in such a way that enormous amounts of energy are released, the fact that the universe's physical laws allow for such things. These are not mistakes in the cosmos. They are not errors or exceptions. They are features. They tell us something true about how reality works. They tell us that the universe is capable of creating things far more extreme and far more magnificent than our everyday experience would suggest. Now, imagine yourself continuing to contemplate these questions, sitting with the wonder, allowing your mind to drift through these cosmic landscapes. Imagine understanding not just the facts about quasars, but the deep significance of what they represent, what it means for the universe to contain such objects, what it means for us, small inhabitants of a small planet circling a medium-sized star, to be capable of discovering and understanding these distant objects. There is something profoundly moving about that realization. There is something that touches something deep within us when we contemplate the universe in this way. As we continue our journey together, as we move forward into deeper and deeper exploration of what quasars are and why they matter, I encourage you to maintain this sense of wonder. Don't let the explanations and the mechanisms and the scientific details overwhelm the fundamental sense of awe that comes from contemplating the cosmos. The science enhances that awe rather than diminishing it. Understanding how quasars work doesn't make them less amazing, it makes them more amazing. It shows us that reality is even more profound and more subtle and more beautiful than we might have imagined, and perhaps that's the deepest lesson that quasars have to teach us. Perhaps that's why they're worth our contemplation. They remind us that the universe is inexhaustibly strange and magnificent, endlessly creative, endlessly surprising. They remind us that questions matter more than certainty, that wonder is more valuable than complacency, that the urge to understand is one of the most fundamentally human things about us. Before we move deeper into the specific mechanisms that power quasars, before we explore in detail the black holes and accretion disks and relativistic jets that create these objects, let me ask you once more to reflect on what you've learned so far. What has resonated most strongly with you? If you're still with us, if the mystery of quasars has captured your imagination and held your attention through this opening exploration, then you're part of something special. You're part of a community of people who care about understanding the universe, who find meaning in asking questions, who are willing to slow down and contemplate deep mysteries. That community is real. It extends around the entire world. It includes scientists and philosophers and artists and dreamers and seekers of all kinds. And your participation in it, your willingness to engage with these ideas, your curiosity and your wonder, these things matter. They matter more than you might think. In a world that often pushes us towards superficiality and speed, the act of sitting quietly and contemplating the cosmos is an act of resistance and an act of profound meaning. So I want to ask you to comment below. Tell us what you found interesting so far. Tell us what questions have come up for you. Tell us where you are in the world, what time it is for you, what drew you to these questions about the universe. Your voice is part of this conversation. Your perspective enriches this entire exploration, and we want to hear from you. We want to know what resonates with you about these distant, impossible objects shining across billions of light years of space, because the cosmos belongs to all of us. Every human being who has ever looked up at the night sky and felt that sense of wonder, that sense of questions larger than themselves, is part of the same conversation that's happening right now. You're not alone. You're part of something ancient and ongoing. You're part of humanity's eternal conversation with the cosmos. So as we move forward into the next stage of our exploration, where we will examine more carefully the cosmic context in which quasars exist, where we will explore the structure of galaxies and the distribution of matter across the universe, where we'll see how quasars fit into the larger story of cosmic evolution, I want you to carry forward this sense of wonder. Carry forward this recognition that we're exploring something profound. Carry forward the recognition that you're part of a universe far larger and far more magnificent than your everyday experience usually reveals. And recognize that the light from these distant quasars has been traveling through the darkness of space for billions of years, across billions of light years of cosmic distance, carrying information about the early universe to us here on this small planet. That light is ancient. It carries within it the secrets of how the universe was in its youth, and we are privileged to be able to decode those secrets, to understand what that light is telling us, to connect with a universe so vast and so old that our minds struggle to comprehend it. Yet we do comprehend it, at least partially, and in that comprehension, we find wonder, we find meaning, we find our place in something larger than ourselves. And that perhaps is the greatest gift that the cosmos can give us, the recognition that we are part of something vast and ancient and beautiful, and that our curiosity, our questions, our hunger to understand connect us to that larger universe in ways that are both humbling and profound. And now, as we prepare to deepen our understanding of the cosmic context in which quasars exist, as we prepare to explore the vast structures of galaxies and the distribution of matter throughout the universe, I want to remind you that this journey is one that unfolds at its own pace. Don't rush. Don't feel pressured to understand everything immediately. Science is not about reaching quick conclusions. It's about careful observation, patient questioning, and allowing understanding to deepen gradually over time. As you watch, as you listen, as you contemplate these ideas, let your mind wander through the cosmic landscape. Let your imagination paint pictures of distant galaxies and bright quasars and black holes spinning in the darkness. Let the wonder of it all wash over you. And then, when you're ready, when you've absorbed what we've shared so far, move forward with us into the next stage of our exploration. The universe will still be there. The quasars will still be shining their ancient light across the cosmic distance. And the questions will still be waiting, patient and eternal, for us to contemplate them. So let's continue together into deeper understanding, into a more detailed exploration of what the universe is actually made of, how it's structured, and how quasars fit into that larger cosmic story. The journey continues, and the best part is yet to come. Before we move forward, let me say once more how much I appreciate you being here with us on this journey. There's something special about an audience that cares deeply about understanding the cosmos, that's willing to slow down and contemplate mysteries, that wants to look beyond the superficial and into the profound questions that drive science and philosophy and our search for meaning. You are that audience, you are people who matter, and we're honored to bring you this exploration. So with that gratitude, let's turn our attention now to the broader cosmic context. Let's explore the vast architecture of the universe itself, the distribution of galaxies across space and time, the grand structure within which these quasars shine. Because to understand quasars, we must first understand the universe they inhabit. We must understand galaxies. We must understand the cosmic web. We must understand the universe's past, present, and future. And in that understanding, the quasars will reveal themselves to us with even greater clarity and beauty. So let's begin this next stage of our journey together, and let's see what the universe wants to show us. The universe, when viewed on the larger scales, reveals a structure of breathtaking organization and complexity. Galaxies are not distributed randomly throughout space. They are organized in a cosmic web, connected by filaments of matter, arranged in ways that suggest deep underlying principles governing how the universe is put together. When astronomers began to map the positions of galaxies in the universe, when they began to measure their distances and positions relative to each other, a remarkable pattern began to emerge. Galaxies tend to cluster together. They form groups and clusters held together by gravity. These clusters of galaxies are themselves organized into larger structures called superclusters, and these superclusters are arranged in a cosmic web with vast voids between them, regions of space that contain relatively few galaxies, surrounded by filaments where galaxies are abundant. It's like a three-dimensional foam with dense regions and empty regions, with structure on every scale you look at. This cosmic web is a fundamental feature of the universe. It's the result of how matter distributed itself in the early universe, how gravity amplified tiny density variations until they grew into the large-scale structure we see today. The Milky Way, our own galaxy, is not isolated in space. It's part of a group of galaxies called the Local Group, which contains several dozen galaxies. The two largest members of the Local Group are the Milky Way and the Andromeda Galaxy. The Milky Way and Andromeda are actually on a collision course. Billions of years from now, they will merge together, eventually forming a single, larger galaxy. This merging process will be dramatic but not catastrophic. When galaxies merge, the stars within them usually don't collide with each other directly. Space is vast and stars are small and far apart. But the gravitational interactions between the two galaxies will be profound. The shapes of both galaxies will be distorted. Stars will be thrown into new orbits. The central supermassive black holes of both galaxies will eventually merge at the center of the newly formed galaxy. It will be a cosmic event of tremendous significance, at least to any observers present to witness it. And this process of galaxy merging has happened many times in cosmic history. In the early universe, galaxies were smaller and closer together. Mergers were more common. Smaller galaxies merged together to form larger ones. Supermassive black holes collided and merged. Through this process of hierarchical merging, galaxies have grown and evolved over billions of years. The largest galaxies we see today are probably the result of numerous mergers. They've accumulated mass over cosmic history by absorbing smaller galaxies. And the supermassive black holes at their centers have grown as well, as they've absorbed black holes from the galaxies they've consumed. This process of galaxy evolution and merging is crucial to understanding quasars and their role in cosmic history. When two galaxies merge, when the process of gravitational disruption and star formation and black hole interaction happens, the supermassive black holes at the centers of those galaxies are sometimes activated. They begin to feed on material. They begin to accrete matter at high rates, and when a supermassive black hole is actively accreting material, it becomes a quasar or an active galactic nucleus. The merger process can trigger quasar activity, and in the early universe, when galaxies were smaller and mergers were more frequent, quasar activity was therefore more common. That's one reason why we see so many more distant quasars, and thus quasars from earlier in cosmic history, than we see nearby quasars. The activity triggered by mergers has diminished over time as the universe has evolved. In the present epoch, most supermassive black holes are relatively quiet. They're not actively accreting material at high rates. But in the early universe, the situation was different. The early universe was a place of tremendous activity and transformation. Galaxies were still forming. Mergers were common. Quasars blazed across the cosmos, brilliant markers of the universe's youth. Understanding this cosmic history helps us appreciate why quasars are so important to astronomy and cosmology. Quasars are not just interesting objects in themselves, though they certainly are that. They're also cosmic beacons, markers of the early universe, windows into how galaxies formed and evolved. By studying quasars, by understanding their properties and their distribution, by mapping how their abundance changed over cosmic time, astronomers can piece together the history of the universe. They can understand how galaxies grew from small beginnings in the early universe to the large structures we see today. They can understand the role that supermassive black holes played in that evolution. They can understand the basic physics that governs the universe on the larger scales. And this is why quasars deserve our contemplation and our wonder. They're not just distant objects. They're chapters in the cosmic story. They're evidence of how the universe has changed and evolved over billions of years. They're proof that the universe is not static and eternal, but dynamic and evolving, constantly changing, constantly being transformed by the interplay of gravity and matter and energy. When we observe a quasar that is billions of light years away, we're observing an object that existed billions of years ago. We are seeing that ancient object as it was in the distant past, and because the universe is so vast, we can observe multiple quasars at different distances. We can see quasars from various epochs in cosmic history. By observing this entire population of quasars, by studying how their properties change with distance and thus with time, we can trace the history of quasars and the history of the universe itself. We can see how quasars were common in the early universe and have become rarer as time has passed. We can see how this correlates with our understanding of galaxy evolution. We can test our models and our theories against the observational evidence. This is how modern astronomy works. We gather data about the universe, we develop theories to explain the data, we make predictions based on those theories, and then we gather more data to test those predictions. It's a process of gradual refinement, of moving closer and closer to an understanding of how the universe actually works. And quasars have been central to this process. They've provided some of the most important data points, some of the most crucial tests of our understanding. So when you look at a quasar, When you contemplate one of these distant, impossible objects, you're not just looking at an individual object, you're looking at a piece of cosmic history. You're looking at evidence of how the universe has evolved. You're looking at a snapshot from billions of years ago of what the universe was like in its youth. That's profound. That's meaningful. And it's one of the reasons why quasars deserve our wonder and our careful attention. They're not just interesting objects, they're fundamental to our understanding of the cosmos. They're essential pieces of the puzzle that is the universe itself. And now, let me ask you once more, if you're still here with us, if this exploration has continued to resonate with you, if you're finding this journey into the cosmos meaningful and interesting, please let us know. Drop a comment below. Tell us what you found interesting in this exploration of galaxies and cosmic structure, and the role of quasars in cosmic history. Tell us what questions have occurred to you. Tell us where you're watching from, what time it is for you, what speaks to you about these distant cosmic objects. Because this is genuinely a conversation. Your engagement matters, your questions matter, your perspective enriches this entire exploration. We want to know what you're thinking. We want to know what captures your imagination about the cosmos. So please, if you're enjoying this journey, if it's meaningful to you, take a moment to engage with us. Like the video, subscribe to the channel, comment and let your voice be heard. Because the cosmos belongs to all of us. Every person who looks up at the sky and wonders about the universe is part of the same eternal conversation. You're part of that conversation. Your voice is part of it, and we want to hear from you. As we continue this contemplation together, let's turn our attention now to the very heart of the mystery. Let's explore in greater depth what happens when a supermassive black hole becomes active, when it begins to feed on the matter around it, when the accretion process transforms a quiet galactic center into the most luminous object in the universe. This is where the real drama unfolds. This is where the extreme physics reveals itself. And this is where we begin to understand why quasars outshine entire galaxies with such apparent ease. The process begins, in many cases, with a collision. Two galaxies merge, their gravitational fields interact, stars are flung into new orbits, gas clouds are compressed and heated, and at the center of this cosmic upheaval, at the very heart of the merging system, something crucial happens. Material from one or both of the galaxies begins to spiral toward the supermassive black holes at their centers. In some cases, this infall of material is gentle and gradual, but in other cases, particularly when galaxies merge violently, the infall can be sudden and dramatic. Large amounts of gas and material are channeled toward the central black hole, and when that happens, when a black hole that has been relatively inactive suddenly finds itself with an abundant supply of food, it awakens, it becomes active, it begins to accrete material at high rates, and in that accretion, it releases energy on a scale that is almost beyond comprehension. The black hole itself doesn't actually shine. A black hole is, by definition, black. Light cannot escape from within the event horizon of a black hole. But the material around the black hole, the matter that is falling toward it, that is being crushed and heated by gravitational forces and friction, that material glows with an incredibly bright light. As material falls toward a black hole, it accelerates. It gains speed. The gravitational potential energy associated with that falling material is converted into kinetic energy, the energy of motion. And then, as material collides with material, as friction works, that kinetic energy is converted into heat. The material in the inner regions of an accretion disk around a black hole can be heated to temperatures of millions of degrees. At these temperatures, the material emits radiation across a broad spectrum. It emits visible light. It emits ultraviolet radiation. It emits X-rays. It emits radio waves. It emits radiation across the entire electromagnetic spectrum. And the total amount of energy being radiated can be truly staggering. A quasar might be converting matter into radiation at a rate of several suns worth of mass per year. That is, several times the mass of our entire sun is being converted into pure energy every single year. The E equals mc squared relationship that Einstein discovered shows us how much energy that represents. The mass of our sun is about 2 times 10 to the 30 kilograms. If you convert even a small fraction of that mass completely into energy, the amount of energy released is astronomical. Quasars do this continuously. They do it on a scale that is hard to visualize, and when you stand back and think about the sheer power involved, When you contemplate what it means for an object to be shining with the brightness of 1 trillion suns, you begin to grasp the extreme nature of what's happening at the centers of these galaxies. But here's something crucial that helps explain how this is possible. Not all of the matter that falls toward a black hole actually falls all the way into the black hole itself. Some of it does, yes. Material does cross the event horizon and fall into the black hole, where it becomes part of the black hole. But before material reaches the event horizon, before it gets that close to the black hole, it encounters powerful forces. It encounters the intense gravitational effects near the black hole, and it also encounters other material that is falling inward. All of this infalling material exerts gravitational pressure, and the result is that the material doesn't fall straight in. Instead, it arranges itself into a disk. The material has angular momentum. It's moving not just toward the black hole, but also around it, in orbit around it. And angular momentum is conserved. The material wants to maintain that rotational motion. The result is an accretion disk, a flattened structure of rotating material surrounding the black hole. In this disk, material is gradually spiraling inward. It's losing energy through friction and radiation. It's slowly making its way toward the center, and as it spirals inward, it gets hotter. The inner regions of the disk are hotter than the outer regions. The material closest to the black hole is hottest, and this is where the most intense radiation is produced. The inner few thousand kilometers of the accretion disk around a supermassive black hole are sites of unimaginable physical extremes. The temperatures are millions of degrees, the densities are incredibly high, the gravitational forces are intense, and the radiation being produced is incredibly bright and incredibly energetic. This accretion disk is not uniform, it has structure. There can be bright spots and dim regions. There can be spiral waves running through the disk, density waves similar to the spiral arms of galaxies. There can be instabilities where the disk becomes turbulent. The material in the disk is not in simple circular orbits. There's heating and cooling happening. There's magnetic field interactions. There are relativistic effects, effects arising from special and general relativity that become important when objects are moving at significant fractions of the speed of light, or when they're in regions of very strong gravity. All of this combines to create a system of remarkable complexity. It's one of the most extreme environments in the universe, and it's the source of the quasar's power. The quasar's brightness comes from the accretion disk. The intense radiation being emitted by the hot gas and material in the disk is what makes quasars shine so brightly. And this radiation is not isotropic. It doesn't radiate equally in all directions. The disk radiates more strongly along its axis than it does in the plane of the disk. There are regions of strong radiation and regions of weaker radiation. The radiation can be absorbed and re-emitted by surrounding material. It can be scattered and transformed, and all of this contributes to the complex appearance of a quasar when observed from Earth. Now, let's talk about something even more remarkable. Let's talk about the jets. Because while the accretion disk accounts for a significant portion of a quasar's radiation, in many cases the jets are equally important, if not more so. These jets are streams of particles and radiation extending from the poles of the black hole and the accretion disk. They shoot outward at nearly the speed of light, extending for millions of light years into the intergalactic medium. They can extend for hundreds of thousands of light years, distances equivalent to the size of dozens of large galaxies placed end to end, and they're incredibly bright. The jets carry away energy from the black hole system and deposit it far away from the central black hole. When you look at many quasars, what you're actually seeing is not just the radiation from the accretion disk, but also the radiation from the jets. The jets are visible as extended structures of bright radio emission. They can be detected at all wavelengths, from radio waves all the way through to gamma rays, and in many cases the jets dominate the appearance of the quasar. They're the most visible features. They're the brightest parts of the system. They're what makes many quasars recognizable as quasars when we observe them with radio telescopes. How do these jets form? What mechanism could produce such powerful directed streams of energy extending for such vast distances? This is one of the profound questions that quasars pose. The answer involves some of the most complex physics in astronomy. The jets appear to be produced by the interaction of the black hole's rotation with the magnetic field structure around it. Supermassive black holes are not necessarily stationary. They can be spinning. They can have significant angular momentum. And when a spinning black hole is surrounded by an accretion disk that also has angular momentum, the two are not necessarily aligned. the disk may be tilted relative to the black hole's rotation axis. The interaction between the spinning black hole and the magnetic field lines threading through the accretion disk can produce a mechanism that accelerates particles and ejects them outward along the poles of the black hole. This is similar in principle to how a particle accelerator works, but operating on scales of light years instead of a few kilometers. The gravitational energy of the system, combined with the rotational energy of the black hole and the energy stored in magnetic fields, is channeled into accelerating particles to near light speeds and ejecting them along the rotation axis of the black hole. The result is the jet. Once the jet is formed, once the particles are being ejected at near light speeds, something even more remarkable happens. The jet interacts with the surrounding material. It plows into the intergalactic gas that exists around the galaxy. The jet creates shocks, sudden regions of intense compression and heating where the fast-moving jet material runs into the stationary surrounding medium. At these shocks, the jet's kinetic energy is converted into heat and radiation. Particles are accelerated to high energies. Radiation is produced, and this radiation is incredibly bright. Many of the brightest radio sources in the sky are jets from quasars and active galaxies. The jets are so bright that they can be detected at distances of billions of light years. They are among the most luminous objects in the universe, and they're produced by the conversion of the gravitational potential energy of infalling material into kinetic energy of the jets, and then the subsequent conversion of that kinetic energy into radiation through interaction with surrounding material. What's particularly fascinating about the jets is something called Doppler boosting. When an object is moving toward you at a significant fraction of the speed of light, the radiation it's emitting appears to be enhanced in brightness and shifted toward higher energies. This is a relativistic effect arising from the special theory of relativity. If a jet is pointed somewhat toward us, if it's moving in a direction that has a component of motion toward Earth, then the radiation from that jet appears to be brighter than it actually is. The observed brightness depends not just on the intrinsic brightness of the jet, but also on how fast it's moving and on the angle at which it's directed toward us. This Doppler boosting effect can amplify the brightness of a jet by factors of 10 or more, in some cases even more than that. So what we observe as the brightness of a quasar is not just the intrinsic brightness of the quasar itself, but also this Doppler boosting effect. The orientation of the quasar relative to us, the angle at which its jets are pointed toward Earth, affects how bright it appears to us. If a quasar's jets are pointed almost directly at us, it appears very bright. If the jets are pointed to the side, it appears dimmer. This is an important recognition because it means that not all quasars are intrinsically equally bright. Some of the brightest ones we observe might owe a significant portion of their apparent brightness to Doppler boosting. They're bright partly because they're intrinsically powerful, and partly because they're oriented in a way that makes them appear brighter to us. This is a humbling realization in some ways. It reminds us that what we observe depends not just on the object we're studying, but also on our perspective, on where we are relative to that object, on the geometry of the situation. When we look at the universe, we're always looking from our particular vantage point. We're seeing things as they appear to us, filtered through the effects of relativity and through the details of the geometry and the distances involved. But it also makes the picture more complex and more interesting. It means that understanding quasars requires not just understanding the objects themselves, but also understanding the relativistic effects that affect how we observe them. It requires understanding the geometry of jets and disks and how they're oriented. It requires thinking carefully about what we're actually seeing when we observe a distant quasar and what's the true nature of the object underlying the observations. As we contemplate these mechanisms, the accretion disk with its incredible temperatures and densities, the jets extending for millions of light years at nearly the speed of light, the Doppler boosting effects that enhance the brightness of jets pointed toward us, the complex magnetic field structures and relativistic effects, we begin to understand the true nature of a quasar. We begin to see how something can shine so brightly across such vast distances. We begin to appreciate the extreme physics that's involved. A quasar is not just a bright object, it's an engine. It's a machine for converting gravitational potential energy into radiation and kinetic energy at an efficiency that surpasses anything else in nature. It's a demonstration of how the laws of physics, when taken to their extremes, allow for processes and objects of truly awesome power and magnitude. and this recognition brings with it a sense of wonder. Here is nature, operating according to principles that we understand mathematically, creating things that are far more powerful and far more strange than our everyday experience would suggest. Here is the universe demonstrating its capacity for extreme creativity and extreme power. I want to pause again and ask you to reflect on what we've been discussing. If you've been following along with us, if you've been imagining these accretion disks and jets, if you've been contemplating the extreme temperatures and densities and speeds involved, if you've been thinking about the sheer power being released, then you're engaging with something profound. You're grappling with the reality of the cosmos, and I'd love to hear what you're thinking. What aspect of the quasar mechanism most captures your imagination? Is it the incredible brightness? Is it the vast distances the jets extend? Is it the extreme temperatures and densities in the accretion disk? Is it the way relativistic effects amplify the brightness of jets pointed toward us? Or is it something else entirely? Drop a comment below and let us know what's resonating with you. What aspects of this mechanism have struck you most powerfully? What questions have arisen in your mind as you've contemplated these extreme objects and processes? Because understanding is not something that happens in isolation. Understanding is something that deepens through conversation, through the exchange of ideas, through thinking together about profound questions. So please, if you're still here with us, if this exploration of quasars is meaningful to you, take a moment to engage, comment, share your thoughts, share what's captured your imagination. Tell us where you're watching from, what time it is for you, how this exploration is affecting you. Your engagement is important, your voice matters, and we genuinely want to hear what you're thinking about all of this. Now let's go even deeper. Let's explore something that might seem almost philosophical in nature, but that has profound practical implications for how we understand quasars. Let's talk about what happens at the event horizon of a black hole, at the boundary beyond which nothing can escape. This is territory that pushes the boundaries of our understanding, that takes us to the edge of what we can know and measure and understand about the universe. The event horizon is not a physical object. It's not a wall or a membrane or anything like that. It's a boundary in space-time. It's a region where the escape velocity reaches the speed of light. If you were somehow able to be at the event horizon, you wouldn't notice anything special happening. Space-time would appear normal. But if you tried to send a signal outward, if you tried to escape, you would find that no signal could reach the outside universe. No information could escape. You would be trapped. Not because there's anything pushing you in, not because there's a force preventing escape, but simply because the geometry of space-time itself is such that all possible paths lead inward. All possible directions, when you account for the curvature of space-time, lead toward the center of the black hole. This is a profound consequence of Einstein's general theory of relativity. The theory shows that massive objects curve the space-time around them. A star curves space-time, a galaxy curves space-time, and a black hole curves space-time in an extreme way. The space-time around a black hole is so severely curved that it creates regions from which nothing can escape. This is not because of gravity as we normally think of it, an attractive force pulling objects downward. It's because of the curvature of space-time itself. Gravity is not a force in the classical Newtonian sense. It's geometry. It's the shape of space-time, and a black hole represents space-time curved to an extreme degree. Now, what happens to material as it falls into a black hole, as it crosses the event horizon and enters the region from which nothing can escape? We don't really know. We can't know in a fundamental sense, because whatever happens inside the event horizon can never send information back out to us. We can't observe it. We can't measure it. We can only theorize based on our understanding of how physics works. According to our current understanding, as material falls into a black hole, it gets more and more compressed. The density increases, the gravitational forces increase, and presumably, at some point the density becomes so extreme that our current understanding of physics breaks down. We reach what's called a singularity, a point where the density becomes infinite, and the laws of physics as we understand them cease to apply. What actually happens at a singularity is not known. Some physicists suspect that quantum gravity effects become important at the scale of the singularity, and that a full understanding would require a complete theory of quantum gravity, something we don't yet have. But here's something remarkable. The fact that we don't know what happens inside the event horizon doesn't prevent us from understanding quasars. It doesn't prevent us from understanding how they produce their tremendous power and brightness. That's because most of the energy that powers a quasar comes from material that hasn't yet reached the event horizon. The energy comes from the accretion disk, from material that's still falling toward the black hole but hasn't yet crossed the point of no return. The gravitational potential energy of material in the accretion disk is released as the material spirals inward, and this energy is what powers the radiation and the jets. The black hole's presence is crucial. It's the black hole that creates the gravitational potential well into which material falls, and it's the strength of gravity near the black hole that allows for the extreme temperatures and densities in the accretion disk. But the specific details of what happens inside the event horizon are not directly relevant to understanding how quasars work. We can understand the power of quasars without needing to understand the interior of a black hole. This is actually a beautiful illustration of how science works. We don't need to understand everything about a system in order to understand some aspects of it. We can observe the effects, we can measure the properties, we can develop models that explain the observations, even if there are aspects of the system that are inaccessible to us. We have learned to work within the limits of what we can know and measure, and by doing so, we can still arrive at profound understandings of how nature works. In the case of black holes and quasars, we can understand the mechanisms that power quasars without needing to know what happens at the singularity inside a black hole. We can understand why quasars shine so brightly. We can understand how they produce jets. We can understand their evolution and their role in cosmic history. And this understanding is based on observations and measurements and careful reasoning. It's grounded in science. This brings us to something important about the nature of scientific understanding itself. Science is not about answering every possible question or understanding every aspect of a system in complete detail. Science is about asking questions that are answerable, making observations that are meaningful, developing theories that can be tested, and refining our understanding based on evidence. Some questions are not answerable, at least not with our current level of knowledge and technology. Some aspects of the universe may be fundamentally inaccessible to us, and that's okay. Science has learned to work within those boundaries. Science has learned to ask the questions that can be answered, and to work toward answering them as thoroughly as possible. And in the process, science has revealed a universe that is far more profound and far more remarkable than any mythology or ancient philosophy could have imagined. The real universe is more strange, more complex, more beautiful than fiction. And quasars are part of that reality. They are real objects, following real physical laws, producing real effects that we can observe and measure and understand. So when we contemplate quasars, when we think about objects that are shining with the brightness of 1 trillion suns, we're contemplating something real. We're not engaging in fantasy or imagination in the sense of making things up. We're engaging with the actual universe as it is, and that actual universe is profound. It's worth contemplating. It's worth our time and our effort and our wonder. Because understanding the universe, grappling with questions about how it works and what it's made of and why things are the way they are, this is one of the most fundamentally human activities we can engage in. It connects us to generations of humans stretching back through history, all of whom have looked up at the stars and wondered. And it connects us to a future in which subsequent generations will continue this same conversation, continue to ask questions about the cosmos, continue to push the boundaries of knowledge and understanding. Now, let's talk about something that might seem almost mundane in comparison to what we've been discussing, but that is actually quite important for understanding quasars observationally. Let's talk about how astronomers actually measure the brightness of quasars and determine their distances. When we look at a quasar through a telescope, when we observe the light coming from a quasar that has been traveling across billions of light years of space, we need to figure out several things. We need to determine how far away it is. We need to determine how much total energy it's radiating. We need to understand its properties. And the tools astronomers use to do this are elegant in their simplicity, even though they rely on sophisticated understanding of how light and matter interact. One of the most important tools is spectroscopy, as we mentioned earlier. When we split the light from a quasar into its component wavelengths, we see a spectrum. And in that spectrum, we see various features that tell us important information. We see absorption lines, wavelengths where light is being absorbed by material between the quasar and us, or by material surrounding the quasar. We see emission lines, wavelengths where material is emitting radiation particularly strongly. And we see the overall shape and intensity of the spectrum, which tells us about the temperature and the physical conditions in the quasar. Most importantly, we see the redshift. The spectral lines are shifted toward the red end of the spectrum compared to where we would expect them to be based on laboratory measurements. This redshift tells us how fast the quasar is moving away from us, and using our understanding of the expansion of the universe, using the cosmological models that describe how the universe expands, we can convert the redshift into a distance. We can determine how far away the quasar is, and from the distance and the observed brightness, we can calculate the total amount of energy the quasar is radiating. We can determine its luminosity. The most distant quasars have redshifts that correspond to distances of over 13 billion light-years. That means the light we're seeing left those quasars when the universe was less than 1 billion years old. We're seeing quasars from when the universe was in its infancy. We're seeing the early universe directly through the light of these distant objects. And this is where quasars become not just interesting objects, but essential tools for understanding cosmic history. By observing quasars at various distances, by measuring their properties, by understanding how those properties vary with distance and thus with time, astronomers can trace the history of the universe. They can determine when quasars were most abundant. They can understand how the quasar population has changed over cosmic time. They can test their models of galaxy evolution and black hole growth. They can understand the role that quasars played in the larger story of how the universe evolved from a smooth, mostly uniform state in the early universe to the complex structure we see today. Quasars are beacons lighting up cosmic history. They're crucial data points for understanding how the universe works. And every new quasar discovered, every new measurement made, adds another piece to the puzzle. Let me ask you once more to engage with this material. If you've been following along, if you've been thinking about the mechanisms that power quasars, if you've been contemplating how astronomers measure the distances to these objects and determine their properties, if you've been imagining the accretion disks and jets and the extreme physics involved, then you're participating in an exploration that matters. You're thinking about real science, about real discoveries about the actual universe, and I want to know what's captured your imagination. What have you found most interesting so far? What questions have arisen for you? What aspects of this exploration are resonating most strongly? Drop a comment and let us know. Tell us what you're thinking. Tell us what you're finding most fascinating about quasars, because this is a genuine conversation. Your engagement matters. Your perspective enriches this entire exploration. And we want to hear from you. We want to know what speaks to you about these distant, impossible objects shining across billions of light years of space. As we continue forward, as we deepen our understanding, I want to emphasize something that might be easy to lose sight of amidst all the technical details. The core mystery of quasars, why they outshine entire galaxies, how something so small can be so bright, this mystery has now been substantially solved. We understand, at least in broad outline, how quasars work. We understand the role of supermassive black holes. We understand the accretion disk mechanism. We understand how jets form and how they shine. We understand the role of relativistic effects and Doppler boosting. We have a comprehensive, scientifically grounded understanding of what quasars are and why they're so bright. And yet, in solving this mystery, we haven't diminished the sense of wonder. We haven't made quasars less amazing. If anything, understanding how they work has made them more amazing. It's shown us that reality is capable of such things. It's shown us that the universe contains such extreme physics, such extreme processes, such extreme objects. It's shown us that nature is endlessly creative, endlessly surprising, endlessly more profound than we might have imagined. And this brings us to something deeper. This brings us to the question of what quasars reveal about the universe itself. Not just what they are and how they work, but what their existence and their properties tell us about the nature of reality. That's where we're going to go next. We're going to explore what quasars reveal about cosmic history, about the early universe, about how galaxies and supermassive black holes have evolved over billions of years. We're going to see how the study of quasars has transformed our understanding of the universe. We're going to understand the profound implications of the fact that quasars exist, that they're as bright as they are, that they were as common as they were in the early universe. These are not just interesting details. These are revelations about the fundamental nature of the cosmos. And as we explore them, as we contemplate them, we'll find ourselves drawn into increasingly profound questions about existence, about complexity, about our place in a universe that is far larger and far stranger and far more wonderful than we ever imagined. So let's continue together. Let's move forward into a deeper exploration of what quasars reveal about cosmic history. Let's see what the light from these distant objects is telling us about how the universe has changed and evolved over billions of years. Let's understand how the most powerful objects in the cosmos have shaped the story of the universe itself. This is the heart of the matter. This is where quasars become not just objects to study, but keys to understanding the universe's deepest secrets. This is where scientific investigation becomes a journey of profound discovery and wonder. As we move deeper into our exploration, we need to understand something fundamental about what the universe was like in its early epochs, before quasars were discovered, before we had the tools to look back so far into cosmic time. For most of the 20th century, before the discovery of quasars, astronomers had a picture of the early universe that was relatively smooth and simple. It seemed that the universe expanded uniformly. Galaxies were distributed relatively evenly. The universe seemed to evolve in a rather straightforward way from the hot, dense state of the Big Bang toward the cooler, more dilute state we see today. But quasars changed this picture. Quasars showed us that the early universe was far more active, far more violent, far more dramatic than this simple picture suggested. The early universe was a place where massive black holes were feeding actively. The early universe was blazing with brilliant quasars. The early universe was a cosmos in transformation, far removed from the relatively quiescent universe we inhabit today. When astronomers began to catalogue quasars systematically, when they began to measure the distances to large numbers of them, a pattern emerged that was striking in its clarity. Quasars were much more common in the distant universe, the universe as it was billions of years ago, than they are in the nearby universe today. This was not a subtle effect. The difference was dramatic. The number of quasars was several orders of magnitude higher in the early universe compared to the present epoch. In other words, the early universe had not hundreds or thousands of quasars, but billions upon billions of them. They were among the dominant luminous objects. If you could somehow travel back to when the universe was a few billion years old, the sky would look very different from how it looks now. Instead of the relatively quiet, slow universe we see today, the universe would be ablaze with the light of billions of quasars. Jets from active galaxies would extend across vast distances. The whole cosmos would be in a state of tremendous activity and energy release. This discovery forced a reconsideration of our understanding of cosmic history. It raised profound questions. What changed? What caused the quasar population to decline? Why are quasars so rare in the nearby universe? What does this tell us about the evolution of galaxies and supermassive black holes? These questions have been at the forefront of observational and theoretical astronomy for decades, and gradually, through careful observation and careful reasoning, astronomers have developed a picture of how the universe has evolved and of the role that quasars and active galaxies have played in that evolution. The picture that has emerged is one of fundamental transformation. The early universe was structured very differently from the universe we see today. In the early universe, galaxies were smaller, they were more numerous, they were colliding and merging at a much higher rate than galaxies do in the present universe. When galaxies collide and merge, as we discussed earlier, the merger process can trigger activity in the supermassive black holes at their centers. The merger can fuel a quasar. In the early universe, with mergers being much more common, quasars were correspondingly much more common. As the universe aged, as the merger rate declined, as galaxies that had been merging gradually merged into larger and larger structures, the quasar population declined. Today, mergers still happen, but they're much rarer. Quasars still appear, but they're far less common than they were billions of years ago. This picture of galaxy evolution through mergers has become known as the hierarchical model of galaxy formation. It proposes that galaxies started out small in the early universe and grew larger over time by merging with other galaxies. The largest galaxies we see today are the result of numerous mergers. They are the end products of billions of years of growth and consolidation, and the black holes at their centers have grown along with the galaxies, accumulating mass as they've merged with other black holes. This model is supported by both observations and detailed computer simulations. Astronomers can simulate the growth of galaxies through mergers in a computer, starting with initial conditions that match what we observe about the early universe. They can track how galaxies merge, how their shapes change, how their black holes grow, and when they do this, they get results that match what we actually observe about the universe. They reproduce the observed distribution of galaxy sizes. They reproduce the observed properties of supermassive black holes. They reproduce the observed history of the quasar population. The simulations show that the universe we see today, with its large galaxies and quiet black holes, is what we would expect from a universe that started with smaller galaxies and frequent mergers in the early epoch. But the implications go even deeper. The connection between galaxy mergers and quasar activity points to something fundamental about the role of supermassive black holes in galaxy evolution. It suggests that black holes are not just passengers in galaxies, not just objects that happen to exist at the centers of galaxies, but have little effect on the galaxy's evolution. Instead, black holes appear to play an active role in regulating how galaxies grow and evolve. When a black hole is active, when it's accreting material and producing a quasar, the jets and radiation from the quasar interact with the surrounding gas and dust in the galaxy. This interaction can have profound effects. The jets can plow through the gas and dust, heating it, pushing it outward, in some cases ejecting it from the galaxy entirely. The intense radiation from the quasar can ionize the gas, changing its physical state, affecting how it can cool and form new stars. The combined effect of the jets and radiation can be to suppress star formation in the galaxy. This is called quasar feedback. The quasar feeds back into its host galaxy, affecting the galaxy's properties, regulating its evolution. This feedback appears to be crucial for understanding how galaxies grow and how they reach the sizes we observe today. Without this feedback, without the regulatory effect of quasars, galaxies would grow much larger than we actually observe. The universe would have fewer large galaxies and more small ones. The properties of galaxies would be very different. So quasars are not just spectacular objects to observe. They're not just bright things that shine across billions of light years. They're integral to the processes that shape how galaxies evolve. They're crucial players in cosmic evolution. They help determine what kind of universe we live in. They help determine the properties of galaxies, the abundance of different galaxy types, the amount of star formation happening at different epochs in cosmic history. Understanding quasars, therefore, means understanding the universe's history. It means understanding how the universe evolved from the relatively smooth, simple state of the early cosmos to the complex, structured universe we see today. Every quasar, every observation of an active galaxy, provides information about this evolutionary process. Every discovery adds to our understanding of cosmic history. Think about what this means from the perspective of deep time. In the early universe, when the universe was perhaps just a few 100 million years old, vast numbers of quasars blazed across the cosmos. These quasars were the products of merging galaxies, of the gravitational interactions and transformations that were reshaping the universe's structure. Through their jets and radiation, these quasars were leaving their mark on their host galaxies and on the intergalactic medium. They were participating in the process that would shape all subsequent cosmic history. As time passed, as the universe aged, as mergers became less frequent, the quasar population faded. The universe became quieter. The brilliant light of billions of quasars dimmed to background. Eventually, by the time the universe reached its current age of about 13.8 billion years, quasars had become rare. Most galaxies, including our own Milky Way, had quiet central black holes. The epoch of brilliant quasars was past. The universe had entered a new phase, characterized by older, more settled galaxies, with mergers and violent activity becoming increasingly rare. And yet, the effects of those ancient quasars persisted. The galaxies they had shaped, the structures they had helped form, the feedback they had provided, all of this had left an imprint on the universe that we can still see and study today. When we observe distant quasars today, when we look at light that left those quasars billions of years ago, we're seeing remnants of this earlier epoch. We're seeing evidence of how the universe was different billions of years ago. We're seeing proof that cosmic evolution has happened, that the universe has changed and transformed over billions of years. And this recognition, this understanding that we're looking at evidence of cosmic change, of the deep history of the universe, this is something profound. It means that the universe has a history. It means that things haven't always been as they are now. It means that the universe is dynamic, evolving, constantly changing and transforming. It means that we are living in just one moment in a vast cosmic story that extends billions of years into the past and billions of years into the future. I want to pause here again and invite you to reflect on what we've been discussing. We've moved from talking about the individual mechanisms that power quasars, the accretion disks, the jets, the relativistic effects, to talking about the role quasars play in cosmic evolution, in shaping how galaxies grow and change over billions of years. This is a shift in perspective. We're moving from asking, how do quasars work, to asking, what do quasars tell us about the universe's history? And the answer is profound. Quasars tell us that the early universe was dramatically different from the universe today. They tell us that galaxies have grown through mergers. They tell us that supermassive black holes have played an important role in regulating galaxy evolution. They tell us that the universe has a history, and we can see evidence of that history by looking at distant objects. If you've been following along with all of this, if these ideas have captured your imagination, I'd truly love to hear your thoughts. What aspect of cosmic evolution speaks to you most powerfully? Is it the idea that galaxies merge and grow through that process? Is it the realization that the early universe was so different from the universe today? Is it the understanding that quasars have shaped cosmic history? What questions have arisen for you? What makes you curious or wonder? Drop a comment below. Tell us what you're thinking. Tell us what's resonating with you about this exploration of cosmic history and the role of quasars in shaping the universe. Tell us where you're watching from, what time it is for you. Share your thoughts and your questions with our community, because this exploration is meaningful, and your voice is part of what makes it meaningful. We genuinely want to hear from you. Now, let's explore something that might seem almost philosophical, but that has profound scientific implications. Let's talk about what it means to understand cosmic history, and how quasars are one of the primary tools we use to do that. Understanding the past is fundamentally different from understanding the present. In the present, we can observe things directly, measure them directly, study them in detail. But the past is gone. We can't travel to the past. We can't measure it directly. All we have is evidence that the past has left behind. The universe, fortunately, is kind enough to preserve evidence of its past in a way that we can study. The most important evidence is light. Light carries information about objects across billions of light years and across billions of years of time. By studying the light from distant objects, we can learn about those objects. By comparing light from objects at different distances, we can compare how the universe was at different times. This is how we study cosmic history. We're not traveling to the past. We're using light as our time machine. We're letting the universe show us its history through the radiation that reaches us. But there's a crucial point here. When we observe a distant quasar, when we see light that left that quasar billions of years ago, we need to be careful about the interpretation. The light we see tells us about that particular quasar as it was billions of years ago. It doesn't tell us directly about how that quasar might have changed since then. It doesn't tell us whether that quasar still exists today, or whether it faded billions of years ago. All it tells us is what that quasar was like at the moment the light was emitted. So when astronomers compare quasars at different distances, they're comparing quasars from different epochs in cosmic history. They're comparing how the quasar population was when the universe was young to how it is now, as the universe is much older. They're building up a picture of cosmic history by assembling observations from many different objects at many different distances. This is called the cosmic archaeological method. We're digging through the layers of the universe, observing objects at different distances and thus at different times in cosmic history, and piecing together a picture of how the universe has evolved. And this method has been remarkably successful. It's led to a detailed understanding of cosmic history, going back to just a few 100 million years after the Big Bang. We have observations of quasars from when the universe was less than 1 billion years old. We have a relatively continuous record of how the quasar population changed as the universe aged. We have information about how galaxies were formed and evolved. We have evidence for how supermassive black holes have grown. All of this comes from the observational record, from the light of distant objects reaching us across billions of light years and billions of years of time. It's one of the great achievements of observational astronomy. And it all rests, in a fundamental way, on the discovery of quasars and the subsequent development of our understanding of what quasars are and what they reveal about cosmic history. There's something almost poignant about this. The quasars that we observe today are ancient objects. The light we see left them billions of years ago. In some sense, we're not observing the universe as it is now, at vast distances. We're observing the universe as it was, in the distant past. We're looking at a universe that has long since evolved beyond the state we're seeing. The quasar we observe today might have faded billions of years ago. The galaxy that hosted it might have changed dramatically, but the light from that ancient quasar carries with it information about how things were in that earlier epoch. And by collecting many such observations, by building a statistical picture from many individual objects, we can understand how the universe has evolved. We can understand the arc of cosmic history. We can understand that the universe is not static and eternal, but dynamic and evolving, changing and transforming over billions of years. This realization has profound philosophical implications. It tells us that the universe has a history. It tells us that present conditions are the result of past processes. It tells us that things haven't always been as they are now and won't always be as they are in the future. It connects us to the deep past of the cosmos. It helps us understand that we live in a universe that has been evolving, changing, and transforming for billions of years. It helps us recognize that the conditions that allowed for the emergence of life, the conditions that allowed for the existence of Earth and the Sun and ourselves, were the products of billions of years of cosmic evolution. We exist because the universe evolved in a particular way. We exist because of events that happened billions of years ago, long before our solar system formed, long before life emerged on Earth. The quasars we observe are evidence of those ancient events. They're witnesses to the early universe. And by studying them, we're in a sense participating in a dialogue with the cosmos about its own history. Let me ask once more, if you're still here with us, if this journey through cosmic history, if this exploration of what quasars reveal about the universe's past has captured your imagination and your wonder, please let us know what aspect of this cosmic history most strikes you. What question has most powerfully arisen in your mind? What makes you most curious about the universe's deep past? Drop a comment, share your thoughts, tell us where you are, what time it is for you. Tell us what this exploration means to you. Because the cosmos belongs to all of us. Every person who wonders about the universe is part of this same eternal conversation, and your voice, your perspective, your questions, they're all valuable. They're all part of what makes this exploration meaningful. So please, engage with us. Comment, share. Tell us what you're thinking, because we genuinely want to know. We want to hear what resonates with you about these ancient objects and what they reveal about the universe's history. Now, let's turn our attention to something that might seem like a technical detail, but that actually opens up to profound questions about the nature of evidence and understanding in science. Let's talk about how we know how far away quasars are and how this knowledge is crucial for understanding their true brightness and power. This is important because distance is fundamental to understanding quasars. If a quasar is farther away than we think, then its true brightness is greater than we calculated. If it's closer than we think, then its true brightness is less. Measuring cosmic distances is one of the fundamental challenges in astronomy, and for distant objects like quasars, it's particularly challenging because we can't use simple methods like parallax, measuring the apparent shift in an object's position as Earth orbits the Sun, which works well for relatively nearby stars. For distant objects, we need other methods. One of the most important is the redshift method, as we've mentioned. By measuring the redshift of a quasar's spectrum, by determining how much the spectral lines are shifted toward the red end of the spectrum, we can determine how fast the quasar is moving away from us. And using our understanding of the expansion of the universe, we can convert that recession velocity into a distance. The expansion of the universe is itself a profound discovery. The universe is not static, it's expanding. Galaxies and quasars are moving away from each other as space itself expands. This expansion was discovered by Edwin Hubble in the 1920s, and it fundamentally changed our understanding of the universe. Hubble found that the more distant a galaxy was, the faster it was moving away from us. He measured the distances to galaxies using a technique called the cosmic distance ladder, a method involving observations at progressively larger distances, using one set of observations to calibrate the next. And he found that the recession velocity was proportional to distance. This is now known as Hubble's law, and it's one of the foundations of modern cosmology. Hubble's law tells us that the universe is expanding in a uniform way. The expansion is described by the Hubble constant, a number that relates recession velocity to distance. If we know the Hubble constant, and if we measure the recession velocity of a distant object through its redshift, we can calculate its distance. Now, the redshift method depends on this understanding of how the universe expands and on the value of the Hubble constant. And it turns out that measuring the Hubble constant precisely has been one of the great challenges of modern astronomy. Different measurements have given slightly different values, and this matters because the value of the Hubble constant directly affects the distances we calculate for quasars and other distant objects. If the Hubble constant has one value, then a quasar with a particular redshift is at one distance. If it has a slightly different value, then the quasar is at a slightly different distance, and this affects the calculation of the quasar's true brightness. So precise measurement of the Hubble constant is crucial for understanding quasars accurately. This is why astronomers have devoted significant effort to measuring the Hubble constant more and more precisely. They use various methods, each with its own advantages and limitations, and gradually, through accumulated measurements and careful analysis, the value of the Hubble constant has been determined more and more precisely. Modern measurements place it at approximately 70 km per second per megaparsec, though there are some tensions between different measurements, with some giving slightly higher values and some giving slightly lower values. These tensions are currently an active area of research in cosmology. Different measurement methods sometimes give somewhat different values, and understanding why this discrepancy exists is an active area of investigation. But the important point is that we can measure cosmic distances using the redshift method, combined with our understanding of the Hubble constant. This method is not perfect, there are systematic uncertainties and potential biases, but it's the best we can do for very distant objects, and it's remarkably successful. It allows us to determine distances to quasars that are billions of light years away. It allows us to build up a picture of how the universe is structured on the larger scales. It allows us to understand cosmic history by comparing quasars at different distances and thus at different epochs. And this is made possible by a combination of careful observations, theoretical understanding of how the universe expands, and clever reasoning. It's a beautiful example of how science works. We can't directly measure the distance to a quasar billions of light years away, but we can measure its redshift. We can understand the physical principles underlying redshift and cosmic expansion. We can use that understanding to calculate the distance, and by doing so, we extend our knowledge of the universe far beyond what direct measurement would allow.